Hello everyone, and once more, welcome to the webinar on what's new in Itasca Software version 9.3. My name is Andrey Pyatigorets, I'm a senior geomechanics software engineer at Itasca, and Jim Hazzard, Itasca Software Manager, will also join and help me to cover all the topics we would like to present today. Alright, first, just a few words about point releases, somewhat a reminder of what it is about. Version 9.3 is our third point release that we have done since version 9.0, and it is third release in the last 18 months. Point releases are a bit of a departure for us, as we traditionally just done major releases approximately every 3 years. The purpose of the point releases is to try to get new features out to the users faster. So rather than, for example, having to wait for 3 years for a major release with large number of new features in it, we are pushing out smaller releases faster, so users can get new features soon after they are developed and tested. All features that appear in point releases will eventually be added to the next major release. A couple of things to note. Point releases are only available through subscription and maintenance plan. Everyone who has subscription can get point releases as soon as they are available. As for people with perpetual licenses, they can get the maintenance plan, which will allow them to access point releases for the duration of that plan. Another important note to make is that point releases are same as big releases in terms of back compatibility. That means that all the save files and data files from previous versions can be opened and run in the latest point release. Here's the outline for the presentation. We will cover several new examples in FLAG2D and FLAG3D. We will talk about a few new features in FLAG2D Sketch, in particular Distinct Fracture Network Generator and Voronoi Block Generator. And these functionalities come together with Joint Set Generator, which was also slightly improved. All of these functionalities have the same look and feel. I will also briefly talk about a couple new functionalities to generate edges from a table in Sketch and generate zones from a topography information. Jim will talk about new Rapid tool, cable bolt pullout calibration tool. He will mention new bar chart for 1D structural elements in FLAG3D and 3DEC, and also we'll talk about velocity weakening joint contact model in 3DEC. As for the examples, they're all available at the Itasca documentation website, which is docs.itascacg.com. Navigate to example applications under FLAG2D, FLAG3D section, and you can find all the new examples that are shown surrounded by the red boxes here in this section. We will cover these 4 examples during the slideshow, and for the last 2 examples, I will show a demo. Let's start with an example of installation of a triple anchored excavation wall. This is actually a classic example that is also available in FLAG version 8.1 and FLAG3D, and it is based on a benchmark case of a deep excavation in Berlin sand, which was originally published by Schweiger in 2002. The example illustrates the applicability of the plastic hardening model for deep excavation problems. Because of this example is available in various studies and various sources, I will not go into any details about it. I just will mention that the example consists of multiple excavation stages, dewatering stages, installation of diaphragm wall, and installation of pretension tankers, and of course cycling to equilibrium after each stage. The anchors are modeled by cable structural elements in FLAG2D, and the diaphragm wall for this particular case is modeled by a layer of elastic zones, even though it can be modeled by beams or liners. Here you can see some of the results from simulations, FLAG2D simulations. And the only thing that I would like to mention here that all these results are consistent with those from other studies and consistent with measured wall deflection presented here. All right, next example is tailings dam static liquefaction example. This example demonstrates the analysis of static liquefaction potential due to stage construction of additional layers in a tailings dam. The model uses small strain and fluid logic to calculate the flow and create and track the phreatic surface. Tailings material is initially assigned the Coulomb model, after which it is changed to North-End model to analyze the potential for static liquefaction. The model starts with generating a starter dam, and then additional tailings are added alongside with dikes to simulate multiple stages of construction. Initially, all the zones of the model except for the starter dam are nulled, as shown here, and the stage construction is simulated by reassigning the null zones to non-null material to simulate adding new stages like dikes and tailings. Here you can see snapshots from simulating 3 different stages. The model is solved to mechanical equilibrium after each stage. When the model is fully constructed, fluid boundary conditions are assigned in terms of fixed water table on the left side of the model and 0 pore pressure on the top. And then we solve the fluid model. In general, we are not interested in the transient response of this model and only need to get the steady state solution at large time. However, since the unsaturated flow model is present, the nonlinear solution is found through a new scheme, which is iterative Picard scheme implemented through zone fluid steady state command. This command is new, starting from version 9.1. And it's a pretty powerful command that allows solving models like this almost instantly to the steady state. Here you can see the contours of saturation at the steady state, and you can also plot contours of pore pressure. Finally, when fluid model is solved, we bring it once more to mechanical equilibrium. To analyze the potential for static liquefaction, the Coulomb model for tailings is not sufficient because it does not incorporate the state parameter and cannot distinguish between dilative and contractive behavior using only one set of material constants. Because of this, Coulomb model is changed to North-End model with additional strain softening material behavior, and all the tailings material is substituted to North-End model. After North-End model, parameters are assigned and initialized based on the existing stress state. A relatively quick surcharge in terms of normal stress is applied at the top surface of the upper tailing. This surcharge can simulate construction of another tailing or any other vertical stress applied to the top portion of the model. And after that, the model is cycled over a certain number of steps, and it can be observed that the top portion of the model is experiencing accelerating motion. In general, this is an indication of failure, and alongside with formation of the shear bands, as shown here, we can see that failure is indeed occurring. And here, actual magnitude of displacement doesn't matter, as it will continue increasing with further cycling. However, accelerated rate of displacement is a good indicator of model instability and overall failure. This concludes the second example, and now let's switch to GEOM and talk about 2 other new examples.
Okay, this is Jim Hazzard, and I'm going to take over talking about the next 2 examples. The first one is rainfall on a slope, and this is a FLAC2D example. Before I get into the example itself, I need to give a little bit of background. So this is a result of some changes and improvements we've made to the fluid flow logic, starting with version 9.1. So you may have seen this before, but from version 9.1 and beyond, one of our major focuses was to try and make the fluid flow logic easier and faster. And so part of that was to make the command simpler and make things easier. And part of that was to make things faster by using, number 1, a steady state solver, and number 2, an implicit solver. And both of these things are new in version 9.1 and beyond. So you may have seen this before. I won't talk a lot about it, but just to summarize, this is an example of a slope. It's actually a landfill. And what we have here is materials of very different permeabilities. So you can see on the left here, there's clay, there's rock, there's sand, and there's waste. And these things have permeabilities that are an order of magnitude difference. And these types of problems are a little bit challenging with the explicit fluid flow approach because the time step depends on the most permeable layer. And so it can take quite a long time to solve these things. So this is the motivation for adding the implicit solver and also the steady state solver. So for this particular example, it's a relatively small example. It's 2D. So it only takes 42 seconds to solve this thing with the regular old explicit approach. But if we use the new implicit approach, it's almost 10 times faster. And if we use the steady state approach, so if you only care about the pore pressures at infinite time, you don't care about the transient, you can get to the steady state almost instantly. In this case, about 100 times faster than you could solve it before. So again, this is a simple example, but you can imagine if you had something that was large in 3D, these sorts of speed ups are fairly significant. Okay, that doesn't have anything to do with the example I'm going to talk about. That's just background, but some of the other changes that we made in version 9.1 are related to the example I will talk about in a minute. And this is the addition of different soil saturation suction models. So what this is about is the relationship between the water content or the saturation and the negative pore pressure, right? And so it is known that in soils that there is some relationship between the saturation and the suction, the negative pore pressure, and depending on the amount of clay content, you see these different types of curves where you can build up quite a lot of suction, right? And this can definitely be important in the stability of slopes and things like that, and that's what I'm going to show in a minute. In version 9 and previous, we always had this kind of relationship here, shown by this orange curve, where you specify some sort of cutoff, some sort of maximum tension that the pore pressure can support, and then as soon as you hit that value, it starts to desaturate, and you don't get any increased suction. You just start to get desaturation. And that's fine in a lot of cases, but often, especially when you have soils with a lot of clay content, you want to have a different sort of curve where when it starts to desaturate, you actually can support more suction. And so we've added in version 9.1 and beyond, we've added these other options here where you can specify the Gardner curve, the Brooks-Corey curve, and the Van Gunchten curve. And this one in red, the cutoff is what has always been there, okay? If you don't like any of these ones that we give you, you can just create a table and create whatever kind of relationship you want. And so these kinds of curves are shown here in this plot on the bottom right. In addition to specifying the relationship between saturation and suction, you can also now specify the relationship between permeability and suction. And so in the past, we've always given you this curve here shown by the equation. It looks like this. And so as the saturation decreases, the permeability also decreases. So this makes sense, and this curve is fine most of the time. But sometimes you want to have a little bit more control over this relationship. And so you can now specify a table and get whatever relationship you want between the relative permeability and the saturation. Okay, so this is all background for the example that I'm actually about to show. So this is an example from the old FLAC, FLAC 8.1. And in FLAC 8.1, they use the two-phase flow option. So those that are familiar with the old FLAC may or may not know that there's a two-phase flow option that allows you to do these types of different relationships between saturation and suction. With the addition of these curves and this flexibility in version 9.1 and beyond, you don't really need the two-phase flow option for civil engineering type problems, right? So where you've got water and air, the two-phase flow option is not really necessary because we have this power to specify these different relationships. And so that's what I'm showing here with this example. The example is a slope. You can see it here with some relatively small amount of rainfall. which is happily stable, sitting there. And then what we're simulating is a large rainfall event, which changes the sort of saturation here, and then you can see what happens. So for this particular example, we're using the Van Gunchten soil suction behavior. So you give a couple of parameters and you end up with a curve like this, where you can see the relationship between the saturation and the suction. And as the saturation decreases, you actually get quite a lot of suction, and this suction actually improves the stability of the slope. We also use a table to specify the relationship between permeability and saturation. So again, as the saturation decreases, the permeability also decreases, and this is potentially important as well. So this is the plot I showed before. This is the slope with 84 millimeters per month of rainfall. So you just give a discharge boundary condition on the top surface here. And in this particular case, I can just say zone fluid steady state, right? And it gets to the steady state case almost instantly. And the steady state case looks like this. So the pink line is the water table, and the colors are showing pore pressure. But what you can see is there are negative pore pressures above the water table. There's suction up here in this blue area, and this is giving extra strength to the slope, and it's, in this case, it's stable, right? I can run the mechanical part of this, and it's stable, it doesn't fail, everything's fine. Then what we do is we simulate a heavy rainfall event. So now it's 230 millimeters over 4 days. I think this is based on a real life example. So you can see I've increased the size of the arrows here just to show you what's happening. These arrows should actually be much bigger compared to the previous arrows, because this is a significant increase in the discharge that we're applying to the top surface here. In this case, I'm not using the steady state command because this only occurs for 4 days. So I'm running it in a transient manner out to 4 days to see what happens after day 1 and day 2 and day 3 and so on. What you can see is that after 4 days of this rainfall, we get a fairly significant change in the pore pressure, which makes sense. But what happens is, because the pore pressure increases and the saturation increases, this is the important part, there's an increase in the saturation, which causes less suction, okay? And remember, it's the suction that is holding the slope together. If we reduce the suction, then the whole thing becomes unstable, and you see this sort of slope failure caused by the reduction in the suction. And so this heavy rain event essentially causes the slope to fail. And then just to emphasize, these plots are showing saturation. So you can see the initial steady state here. Obviously below the water table, the saturation is 1, and above the water table, the saturation decreases. And up in this blue region, it's like, 0.6. When we put on the heavy rain, what you can see is that the saturation increases, especially close to the surface here. Now in this yellow region, it's like 0.8, 0.9. And because the saturation increases, there's less suction, and the whole thing fails. And so this is just an example showing you how you can do these types of problems in the new FLAC 2D and in fact 3D without using two-phase flow. Okay, next example. This one's quite different. Factor of safety for a jointed rock slope. So if you haven't seen it already, in the previous version of FLAC 2D, we added this joint set generator. This is kind of mimicking UDEC functionality. It allows you to create edges in Sketch and then turn these edges into joints. And so you have the ability to set different spacings and different orientations and even different continuity of the joints when you're creating them in Sketch, and then you can turn them into joints and run these models. So this logic has existed for a couple of versions now, but we've used this to create a new example that's new in 9.3. So the new example comes from UDEC, and what it is a bunch of different slopes with different joint orientations and different potential failure mechanisms. And we just look at how this behaves in FLAC 2D. And so the results look like this. This is plotting displacements, contour by displacements, and displacement vectors. So you can see the failure mechanisms here when there's sliding along the joints and some failure in the continuum. You can see the factor of safety, and you can see the comparison of factor of safety in FLAC 2D compared to what we got in UDEC. Here's some of the other examples. This one's toppling, and this one's toppling with blocks, and then this is this other interesting sliding mechanism. This is showing exaggerated deformation. So note that these were all run in small strain. And then the deformation that you're seeing here that shows this bending and so on is exaggerated deformation. So it works pretty well. Just a couple of words about comparing with UDEC. The factor of safety is quite similar to what we got with UDEC. The failure mechanisms are very similar. I haven't shown the plots here, but the nature of the failure in these things is very similar. But one important thing to note is that these FLAC 2D models run significantly faster than the equivalent UDEC models. And the other thing to note is that you can't do everything in FLAC 2D that you can do in UDEC. We still do not yet have the ability to run these things in large strain, and we do not yet have the ability to do fluid flow in the joints. Okay, I'm done with that part. I will now pass it back to Andrey.
Thank you, Jim. And now let's talk about some of the new features in version 9.3. I'm going to start with Discrete Fracture Network and Voronoi block generators in FLAC2D sketch. For this, let me actually switch to FLAC2D and demonstrate how these tools work. I'll start with an empty project. I'm just going to click on Cancel here, and it will create an empty sketch worksheet. And let's just create a simple tunnel geometry using Tunnel Wizard. Let's create a tunnel like this with all the default parameters. All right, it looks good. Let's select all edges and assign group name tunnel to them, so we can easily identify them later. And let's create a box around the tunnel so we can have a domain. Just a simple rectangular box. So now we got our tunnel, our box, and we can fill this box with Discrete Fracture Network. For this, we have a new wizard that's called Fracture Wizard. That's how it looks. It has several or multiple options here. The first thing to do is to select the domain where we want to create fractures. For example, we can select closed polygon, and that can be one of these two in this case. And when we click on one of these domains, it got highlighted in blue, meaning that the domain got selected and it will be used to create fractures in it. Overall, the fracture logic is based on existing discrete fracture network functionality available in FLAC2D and FLAC3D. And you can read about this functionality in Itasca documentation. It's located under Common Commands and Fish. Let's go back to our example. We can see that next group of options, it's general group. We can select random seed for different distributions that will be used for different distributions. And for example, for deep angle, let's use Gaussian distribution with around, let's say, 45 degrees with standard deviation of 30 degrees. And we can also specify other parameters, including size of the fractures. Let's use between 1 and 10 units. Let's use power law distribution. The next group of parameters, it's generation criteria, including number of fractures that will be generated or fracture density. So let's generate, for example, 1,000 fractures in this example. If we click on the preview button, we can see that fractures got generated for this particular random seed. We can change random seed and generate another distribution. If we uncheck this button, this box, we can continuously generate different distributions. So let's say we are satisfied with our distribution. Let's click on the OK button, and edges corresponding to this distribution will be generated in FLAC2D sketch. It looks a bit congested, so let's change the size of the points and markers. Let's go to right click and go to sketch options, and there's points and mark size. We can reduce it, and now it looks much better. By the way, all the edges corresponding to discrete fracture network go into slot DFN and the group that we assigned, which is DFN1 in our case. And we can see that they're all there. One good thing to do after generation is to do some cleanup. And one of the tools that's already available, it's merging nearly coincident points. Let's merge them within this tolerance. And we can see that 21 points got merged, which would improve mesh quality later. We also currently working on additional tools that will allow further cleanup of the geometry to prevent generation of bad mesh elements, and which would result in poor quality zones. Next step is assignment of zone size. We can go to arrow sizing tool, and we will assign zone length. Let's use 0.2, let's say meters, and let's use at least 2 zones per edge. This is an important parameter because afterwards we would like to do separation between zones along these fractures. So there could be some sliding happening or any other prescribed motion according to different laws. So the separation works much better if we have at least 2 zones on each edge. So let's click on OK. And the next step is mesh generation. It is recommended to generate unstructured mesh for such complex geometries. So let's go to set meshing parameters and create. We will click on create unstructured meshes only. And then we can click mesh now. This will take maybe like 10 seconds on my laptop. And for this fine geometry, I expect we will generate somewhere between 30 and 40,000 elements in this mesh. And we can see that we got warning that at least one of those elements has poor quality, which will result in poor quality zone. However, it's not really a problem for mechanical analysis, but you have to be careful when you run, for example, fluid or thermal or dynamics analysis, because those poor elements may negatively affect the time step. In our case, we can just simply ignore this warning, and we can generate zones out of this geometry. After generating zones, it is recommended to automatically assign groups to the boundaries of the model. So we go into automatic grouping or zone skinning. It's called zone skinning, and we can say ignore existing groups and assign new groups to the boundaries. So we got automatic assignment of all the exterior boundaries of the model, automatic group assignment. Now, if you plot, this is, by the way, model pane. If you plot all grouped faces, we can see that we have our discrete fracture network. By the way, let's click on it and change color so you can see it better. So DFN corresponds to zone faces. We can separate these faces. And we got our exterior boundaries and our tunnel. So that's how you can easily create rather complex DFN geometries using Flag2D Sketch. And with this, let's switch to the next example and see how we can use DFN in actual real example. All right, this is an example of unconfined compressive strength test run on a block of fractured material. And fractures here are created in a manner similar to the one I presented earlier. I created them actually predominantly under 45 degrees deep with a standard deviation of around 30 degrees. I recorded all the information using state record and put it in data file. I mean, all the commands that were issued during the sketch preparation, sketch geometry preparation. And the next step after we created all the geometry is to create zone joints along the fractures. Zone joints are somewhat similar to interfaces, however, they are a bit more superior in terms of resolving complex contacts and intersections between, let's say, faults or fractures, and they're more similar to logic provided in FreeDeck or UDeck. So we configure for zone joints. We create zone joints using by slot keyword, and in this case slot DFN, and we separate all the zones and faces along the fractures. And we also use distinct geometry keyword that specifies that fractures are coming from sketch, and this keyword is imperative to use when you have rather complex intersections. So when we run these two commands, I can execute just these two commands by running selection. All the zones and faces and grid points are separated along fractures, and contacts are created. One important thing to note that zone joins are only operate in small strain right now. We are working on changing the logic to large strain, and default constitutive model for zone joints is Moore model. And next steps, it's to provide material properties for this model, material properties for matrix model. We use Hook-Brown here. And all other commands here are about tracking vertical stress and displacement or strain for this specimen to be able to plot stress versus strain. So let's run this model up to 12,000 steps. We will apply some velocity at the top and bottom boundary, and we'll see how the model runs. So here we can see the contour plot of maximum shear strain increment and plot of shear displacement along zone joints. This plot shows exaggerated displacements because we actually run in small strain, but you can see that there's deformations. It's just because we use deformed factor 5. And here we plot in vertical stress versus vertical strain. We can see that failure already happened. We reached the peak of 3.5 MPa, and now material is shearing along predominantly diagonal fractures, and shear bands are forming in between fractures. I believe there's probably some tensile failure happening as well, but in general we see that under compressive stress, material is failing and shearing in diagonal along the diagonal lines, and we can see that there's multiple shear bands are forming. So this example shows UCS test, and let me show you just one more example, a bit more complex. Okay, here it is. This is an example of an open pit mine excavation and calculation of the factor of safety. It is based on a real engineering project and uses an actual geometry. The model contains a couple of excavated regions up here and a heavily fractured domain adjacent to this large fault. Just for illustration purposes and to promote and exaggerate the failure, I changed some material properties for this lower left portion of the model. However, for a real project, you would need to make sure that any DFN is generated according to available or measured data, as well as material properties for contacts and for zones are calibrated to represent the properties of fractures and rock. Here you can see contours of displacement magnitude and shear displacements at the zone joints after calculation of the factor of safety. This plot represents the first unstable state when material properties were reduced just enough to cause failure. We can see the rotational mechanism of failure happening in this case. And just to remind, the factor of safety calculations in FLAG 2D and FLAG 3D are based on the strength reduction method, and zone joints can be explicitly incorporated into factor of safety calculations, which was done in this case. All right, in summary, this example highlights that DFN can be easily generated and used for larger problems. And now let's switch to the next topic. Now let's talk about the next new feature in version 9.3, which is Voronoi block generator in FLAG 2D sketch. I will show how it works on an example of tunnel for a fractured rock, which is similar to the one presented in documentation. And this example will demonstrate methodology for generating a Voronoi fracture network and its effect on the stability of a tunnel in fractured rock. We will generate Voronoi blocks inside of this interior domain. Let me zoom in. And to generate Voronoi block pattern, we can go to Point Edge tool and select Voronoi block. Here we can see several groups of parameters. First one is about selecting where Voronoi pattern will be created. Let's select this interior polygon. And other group is about its general group, about providing group name, random seed for Voronoi pattern. And let me show you how this pattern may look like for this particular arrangement of parameters. So this would be for random seed 111. We can use any other random seed. Let's go back to the original one. And we can use different patterns like quadrilateral, hexahedral. We can use elongation and inclination. For example, it's going to be like this if we specify these parameters. Same for quadrilateral and same for random. Let's go to our original values and generate Voronoi blocks based on these values. So Voronoi blocks got generated, and now the idea is to insert a tunnel inside of this fractured rock mass represented by Voronoi blocks. However, if we draw a tunnel right here, it's going to be quite cumbersome to assign groups to tunnel walls because tunnel walls will be intersected with Voronoi edges. So we create tunnel in a separate sketch set, and we assign groups right here. We can see that I specify tunnel wall to the group name. And what we're going to do, we're going to copy these edges to the set Voronoi, where we have Voronoi blocks created already. So after we copy, this tunnel appears here. We can check that it's still the group names are assigned. We can highlight them, so they're there. So now let's assign size or length for zones. We will use 0.2 meters and at least 2 zones per edge. All these edges got all the zones or discretizations properly assigned. Now we just need to change the exterior domain discretization. We will use 1 meter discretization on these exterior edges. And now we're ready for meshing. We will use unstructured mesh as before, and just click on mesh now. While the meshing is going, I want to say that we will still need to assign group name to the interior part of the tunnel to be able to excavate it. And this can be done by selecting a single block and then selecting multiple blocks around it in this manner. Of course, I selected a few extra, but I can deselect them, and I can easily assign, for example, group excavate. I can see that I selected a few more, but with careful selection, I can select only necessary blocks and assign group excavation or excavate. So when we complete this task, we can go to the original. I can show you the original example. I saved all the commands issued by Sketch using state record and put them in file geometry. And if I call this, I will produce the same geometry as I showed you earlier. Then the next step would be face skinning to assign groups to the exterior faces of the model. Then we need to configure zone joints and separate zone faces by slot using slot Voronoi and create zone joints along them. Then we initialize all the parameters, assign gravitational, apply gravitational loading, and cycle to initial equilibrium. After that, we excavate the tunnel, and we will see that this will create unstable conditions. And if you look at zone joints, we will see that some of the blocks start sliding along the zone joints, even though this is small strain. We can see that pretty large shear displacements are recorded on zone joints, and some of the blocks moving with accelerating motion. For example, this little block and this block's on the right, but this one obviously is the largest, has largest velocity. So without any support, this particular model is unstable, and that cannot be cycled to equilibrium. However, if we install liner, which we represented in FLAG2D beams, we can see that the model becomes stable. The displacement magnitude is much smaller around the tunnel right now, and overall no blocks are sliding or producing large displacements, large shear displacements. If you look at moment thrust diagram, some of the elements on the line are experiencing a little bit larger forces and moments, but overall the whole liner is within factor of safety 1.1, and majority is actually within 1.2. So this example demonstrates how you can easily generate Voronoi fracture network and use it for simulation of fractured rock. Switching gears from DFN and Voronoi generators, Let me briefly mention a couple other new features in version 9.3. Specifically, in Flag2D, we added capability to generate edges and polylines from a table containing information about 2D points in space. So for example, if we have points defined in a table, I can run the command to import the table, and then I can run command sketch edge create by table, and we will create a polyline from these points. And here for reference, I already imported a DXF containing the same information as the table, and we can see that the results of importing table and DXF are the same. Similarly, we can extend the layer of zones to the topography defined by points, provided we have this table, and the zones will be extended to the topographic surface. So if you run this command, we're going to see that the zones got extended, and we quickly generated zones under the topographic surface using table information. With this, I want to conclude my part, and now let's switch to Jim, and he will show a few more features, and we'll conclude the presentation after that.
Okay, the next thing that I'll talk about is something that we are calling rapid tools. And what this is an initiative to try to create some easy-to-use tools to allow you to do certain tasks without actually having to run any numerical models. So the first one of these you may have seen before. This was released with FLAC version 9.2. But I'll quickly show it again because we have added a couple of new capabilities with this first rapid tool. So if I'm looking at, in this case, FLAC 3D, but this is actually included with all of the software. So here I'm looking at FLAC 3D, and if I'm looking at the workspace and I go up to select content, you will see there's an entry called rapid tools. And right now we have two of them, rock slope and cable pull. It is our intention to roll out more of these as time goes by. For now, I will just talk about these two. So the rock slope tool was released as part of 9.2, but I'll just show you again as a reminder. If you click on that one, let's hide the commands here so we can see everything. So what you see here is a slope, and the purpose of this is to try to calculate the factor of safety for this relatively simple slope in a very quick manner and very easily. And so for this particular configuration, you can see here there's inputs for the geometry, there's inputs related to the water table, and then there's rock properties. This is assumed to be a rock slope. It is a Hooke-Brown material. These are Hooke-Brown properties here. And for this set of properties and this geometry of the slope, it's telling me that there's a factor of safety of 1.8. Now, what I can do is I can just start moving these sliders and see what happens. So let's pretend that the material is actually weaker, so I reduce the unconfined compressive strength, and I can see that the factor of safety is reducing. Now it's at about 1.6. Similarly, I could increase the slope height, see what happens, and then the factor of safety goes down even more, right? So this is all intuitive, but it's a super fast and easy way to get factor of safety for a certain set of parameters and a certain slope geometry. The way this is done is it's using machine learning. So we have run thousands and thousands of these models with different geometries and properties, and then use the magic of machine learning to generate this tool so that you can get the answer almost instantaneously without actually having to run any models. Now, this is super useful, but of course, this model is relatively simple. Maybe you want to do something a little bit more complicated. Maybe you want to start with this model as like a starting point. In version 9.2, you could export a Python script that would build this model for you in 2D. In 9.3, you now have the ability to output a data file that uses fish and create this model in 2D, and you can also create this model in 3D. So I'll quickly demonstrate here. If I hit this button, create FLAC model, I can choose Python or .dat, and I choose export and give it some name. So here it opens the data file. You can see here there's some fish parameters that relate to the quantities from those sliders that I was just showing you. And it uses these parameters to build the slope. set the properties, boundary conditions, water table, so on, and then run a factor of safety analysis. So I can actually run this. Let's bring my commands back. And just quickly, I'll plot it to show you what it looks like. So here's the model that it creates for you. You can see it's 3D model. It's just one zone thick. I can look at contours of displacement. So right now it's doing the factor of safety calculation here. And you can see the displacement's changing as it's doing the calculations. So this obviously takes some time, right? Maybe, I don't know, 5 to 10 minutes to do this, as compared to basically instantaneous when you're doing the rapid tool. So hopefully you can see the value of the machine learning here in solving these simple types of problems. Okay, let me stop that one, and I'll talk about the new tool that we have in 9.3. So if I go back up here and go to Rapid Tools and choose Cable Pull. All right, let's hide some of this to give us some more space. Make this a little bigger. So what this is it's a tool that allows you to figure out the properties of a cable or a bolt or some sort of support system, okay? Now you have a lot of properties that you need to specify when you put cables in your model, or you put bolts in your model, and it's not always easy to figure out what those should be. Usually, well, often what people do in reality is they have pull-out tests. So you have a cable grouted in something, either in the lab or maybe in the field, and you pull on it and you get a plot that looks like this top plot, which is force versus displacement. And so what you see is this kind of behavior where initially you're pulling on it and the force goes up and it's elastic. Then maybe the grout starts to yield, so you see a bend in the curve. Then maybe the steel cable itself yields, and so the curve flattens off, and then maybe you get a rupture and all the forces drop to zero. And so what you want to do is figure out what properties will give you the behavior that you want. Maybe you don't really know the behavior that you want. Maybe you don't have any data. So another thing that we have here is some predefined types of bolts. So if I click on set initial bolt values, I can choose from these different predefined bolts here, right? Rebar number 6, rebar number 8. It changes the properties, it changes the plots. Now, maybe none of these is exactly what you have, but maybe you actually have data that you've recorded from a lab study or a field study. I could actually load that in here. So if I click on load data, I can enter in values here, and this is displacement in millimeters and force in kilonewtons. I can copy and paste from a spreadsheet or something like that. I can type things in here by hand. So just for fun, let's say 0, 1, and then let's say 1 millimeter, I've got 50 kilonewtons of force, and 2 millimeters, I've got 100, and maybe 3, I've got 120. Okay, so now I can see the real life data as this blue line compared to what I would get if I ran this model with these properties. Now, I should tell you this particular rapid tool is not using machine learning. It's actually a semi-analytical solution that assumes infinitely stiff zones and pulling a cable through them, but it definitely gets you close to what you want and is way easier than actually running a bunch of tests in FLAC3D or FLAC2D. So, okay, I've loaded in this data, and now the trick is to try and match it, right? So I can see that this rebar number 6 is actually quite a bit stiffer than the data that I loaded in, so maybe I want to make it less stiff. So let's reduce the cable Young's modulus. Maybe let's reduce the bond stiffness, so I can sort of start to match the data that I read in. I can also see that my cable is too strong here, and there's a bit of a bend in the data, so maybe I can reduce the bond strength so that the grout starts to yield, and then I can see this sort of bending. And so you can play around with these sliders and try to match the data that you read in. And then once you have the data that you're happy with, or the behavior that you're happy with, you can go over here to where it says get commands. Here's the commands that are necessary to assign the properties to a cable that you've created in FLAC3D or Flag2D, or 3DEC, or even PFC. Okay, and then, if you really want to dig into the details, you can start looking at the strain and displacement along the length of the cable, and the forces in the grout and the steel bar along the length of the cable. And you can do that by for different levels of displacement. So if I go here where it says model settings, I can move this displacement slider, seeing it moves this little blue ball around. And so I can see what the profile of forces and displacements look like for different levels of applied displacement to the top of this bar. Okay, so that's this rapid tool. It's just a nice and easy way to try and calibrate the structural elements that you might be using in your model. Okay, that's all I'm going to say about that. Two more things quickly before we wrap up here. Let me just go back to PowerPoint. Okay, just a couple more things to mention that are new in version 9.3. Number one is that we've added the ability to plot bar charts on top of one-dimensional structural elements. So this includes cables, beams, piles, and this is true in Flag3D or in 3DEC or even PFC. So before version 9.3, you could plot your one-dimensional elements and contour them by some quantity, axial force or moment or something like that. This is an example from the manual where there's an excavation and some beams, some vertical beams that are providing some support. And you can see where the high moments are here at the bottom of the excavation. And what we've added in 9.3 is the ability to plot these as bar charts. And so this is just a nice way to be able to visualize what's happening with a little more clarity. You can see, obviously the bar sizes are scaled to the moments in this case, but you could do the same thing with axial forces and so on. So this is just a nice little new feature in 9.3. And then the very last thing I'll talk about is related to 3DEC. And what this is it's a new joint constitutive model in 3DEC. It's a softening type of model. So in the past, we've had models where the friction went from a static level, a fairly high static level, to a lower dynamic level over some specified amount of displacement. So you have this softening behavior. We can now do the same thing, but the friction decreases as a function of shear velocity rather than shear displacement. And so you get a curve like this where the friction decreases as a function of velocity. And so you can get some pretty interesting behaviors here, some stick slip behavior as the friction changes with velocity. Okay, and I think that is all we're going to talk about. And thank you for joining, and now it's time for questions.